What secrets lie within the world of herbal glycosides? In this journey, we'll uncover the types, chemical structures, and pharmacological effects of herbal glycosides, with a special focus on cardiac, cyanogenic, and anthraquinone glycosides. Let's chart our course through the fascinating world of glycosides. We'll begin by understanding what glycosides are, then explore cardiac, cyanogenic, and anthraquinone glycosides in depth. Before we dive into specific glycoside groups, let's lay the foundation by understanding what glycosides are, their basic structure, and the variety found in the plant kingdom. To truly appreciate the role of glycosides in herbal pharmacology, we need to define what a glycoside is. A glycoside is a compound consisting of a sugar moiety, also called the glycone, bound to a non-sugar moiety, known as the aglycone, via a glycosidic bond. This definition is crucial because it highlights the dual nature of glycosides, which underpins their diverse biological activities. Here's how glycosides are classified in plants: saponins, cardiac, cyanogenic, anthraquinone, and several other types, each with distinct chemical features and biological roles. Saponins are triterpenoid or steroidal glycosides known for their soap-like properties. Cardiac glycosides contain a steroidal aglycone and have potent effects on heart function. Cyanogenic glycosides release hydrogen cyanide and can be toxic under certain conditions. Anthraquinone glycosides are derived from anthracene and are well known for their laxative effects. Other types of glycosides include flavonoid, glucosinolate, iridoid, and secoiridoid glycosides, each with unique properties. Let's break down the structure of glycosides. They consist of a sugar part and a non-sugar part, which can be separated by hydrolysis, unlocking their biological activity. The sugar moiety, or glycone, provides solubility and aids in transport within the plant. The non-sugar moiety, or aglycone, is the active portion and determines the pharmacological effect. Hydrolysis breaks the glycoside into its glycone and aglycone parts, typically through enzymes or acids. Cardiac glycosides are among the most medically significant glycosides. In this section, we'll explore their chemical structure, sources, and powerful effects on the heart. Imagine facing the daily challenge of heart failure, where the heart can't pump efficiently and fluid builds up in the body. This is a real-life problem for many, and it's where cardiac glycosides have played a crucial role in orthodox medicine. Let's see how these compounds make a difference. Let's examine the structure of cardiac glycosides: a steroidal aglycone, a sugar chain, and two main subtypes, cardenolides and bufadinolides. The steroidal aglycone forms the core structure of cardiac glycosides and is responsible for their biological activity. The sugar moiety typically consists of 3 sugars, such as glucose, rhamnose, and digitoxose. Cardenolides, with a 23-carbon aglycone, are the main medical group found in plants like digitalis. Bufadinolides have a 24-carbon aglycone and are less common, found in the parotid glands of toads. Here's how cardiac glycosides work. They strengthen heart contractions, slow the heart rate, and improve the heart's efficiency. The positive inotropic effect means cardiac glycosides increase the force of heart contraction, boosting cardiac output. The negative chronotropic effect slows the heart rate and prolongs the relaxation phase, or diastole. The positive tonotropic effect increases the tone of the heart muscle and can reduce an enlarged heart. While cardiac glycosides can be life-saving, their toxicity profile means careful dosing is essential to avoid slowing the heart too much or causing arrhythmias. A negative dromotropic effect slows impulse conduction in the heart, increasing the risk of bradycardia. A positive bathymetropic effect raises the heart's excitability, which can lead to dangerous arrhythmias. Beyond heart conditions, cardiac glycosides may also reduce fluid retention and show promise in cancer research. Cardiac glycosides increase renal excretion, helping to reduce edema by promoting fluid loss. Emerging research suggests cardiac glycosides may disrupt the oxidative state in cancer cells, leading to cell death. Cyanogenic glycosides are both fascinating and potentially dangerous. In this section, we'll explore how these compounds release cyanide, their detoxification, and their roles in herbal medicine. It's a paradox that something as toxic as cyanide could have a place in herbal medicine. How can a toxic compound like cyanide be used therapeutically in herbal medicine? This question challenges our assumptions about natural remedies and highlights the fine line between poison and medicine. Let's look at the chemistry. Cyanogenic glycosides like amygdalin and prunasin release cyanide when hydrolyzed, serving as a natural plant defense. Amygdalin and prunasin are cyanogenic glycosides found in plant families like Rosaceae, Poaceae, and Fabaceae. When hydrolyzed, these glycosides release hydrogen cyanide, a potent toxin. Plants store glycosides and their hydrolyzing enzymes separately, mixing them only when tissue is damaged as a defense mechanism. Here's how the body handles cyanide. The liver enzyme rhodinase converts it to a safer compound, but high doses can overwhelm this system and cause severe toxicity. The rhodinase enzyme in the liver detoxifies cyanide by converting it to thiocyanate, which is much less toxic. Symptoms of cyanide toxicity include dizziness, central nervous system shutdown, and respiratory failure. An antidote for cyanide poisoning involves sodium thiosulfate, which helps convert cyanide to thiocyanate. Despite their risks, cyanogenic glycosides have found therapeutic uses, especially in treating coughs and as alternative cancer remedies. Cyanogenic glycosides can act as expectorants and mild sedatives, making them useful for coughs. They also have digestive and antispasmodic effects, helping to relieve discomfort and muscle spasms. Amygdalin, also known as Letril, has been promoted as an alternative cancer treatment, though its efficacy remains controversial. Anthraquinone glycosides are best known for their role as natural laxatives. Let's explore their chemistry, how they work, and important safety considerations. Let's start with the chemistry. Anthraquinone glycosides have an anthracene backbone, and key examples include imidin and cresophenol. The anthracene backbone, with its hydroxyl and carbonyl groups, forms the core of anthraquinone glycosides. Imidin and cresophenol, found in Rheum palmatum, are examples of dihydroxyanthraquinones. Here's how they work. By stimulating peristalsis and inhibiting water reabsorption, anthraquinone glycosides act as effective laxatives. Anthraquinone glycosides stimulate peristalsis, increasing gut motility and reducing transit time. They inhibit water and electrolyte reabsorption, leading to increased fecal volume and gastrointestinal pressure. While effective, anthraquinone glycosides must be used with caution due to risks of toxicity and specific contraindications. Anthraquinone glycosides are used to treat constipation, hemorrhoids, and anal fissures. However, prolonged use can lead to water and electrolyte loss, muscle weakness, and even changes in bowel structure. These compounds are contraindicated in cases of bowel obstruction, inflammatory bowel disease, pregnancy, and unexplained abdominal pain. Herbal glycosides offer powerful benefits, but demand respect for their risks. By understanding the chemistry and pharmacology of glycosides, we can harness their healing power while respecting their potential dangers. The story of herbal glycosides is a reminder that nature's remedies are both potent and complex.